the number of participants. We encourage all participants interested in a particular mini course to attend all lectures and activities associated with that mini course to get the most out of it. And yeah, with that being said, we are very excited to have Rylee Lyman speaking on Serre theory. Whenever you're ready, Rylee.
Great. Thank you all for coming. So I'm going to tell you about the Serre theory of groups acting on trees, which is some of the math that I like the most. Let me put the link. So I put these notes as they currently are on my website. Let's see. So here's the PDF link. At the end, so I'm going to be marking up what I write. And at the end, I'll put whatever I end up with on there as well. If you happen to use Notability, I'll also give you the note link. I don't even know how that works, but if you know, then you can do you. Okay, cool. So I wanted to start first off, I guess the overview of like why you should care about Serre theory, at least as a geometric group theorist, is that it's really like one of the main inductive tools in studying groups. What Serre theory allows you to do is it allows you to break large groups into smaller pieces, understand the pieces and how they fit together, and I guess hopefully understand something about the group that you started with. So today I want to start with some examples of groups that act on trees, just to see sort of the variety of what's possible. And then I want to give you the formal definition of what a graph of groups is, and how you can associate a graph of groups to an action of a group on a tree. And then we'll state the fundamental theorem at the end. Okay, so here we go. So free groups are maybe the first class of groups that we think of as acting on trees. We learned in our first algebraic topology class that free groups are fundamental groups of graphs. So that means that free groups act on the universal cover of those graphs, and those universal covers are trees. So here's maybe our favorite free group, the free group of rank 2. And I can realize it as the fundamental group of this graph and also this graph fairly easily. And I guess there's a way to go from this graph to this graph by collapsing the green edge. And this graph, I guess, in terms of algebraic topology, does not have fundamental group free of rank 2, but I will tell you a way to sort of collapse the tree that it acts on so that the quotient looks like this. So let's do that. So the universal cover of the graph on the left looks something like this. So remember, our original graph was trivalent, so this graph is also trivalent, and each vertex is connected to one edge of each color. If I were to collapse all of the orbits of green edges, I'll end up with this graph over here. This is maybe the graph that a geometric group theorist thinks of first when they think of the free group of rank 2. This is, I guess, the Cayley graph for a free generating set. And then if I further collapse each red edge to a vertex, what I get is this kind of monstrous looking thing here. Where now I only have all of the blue edges. And so these have finite valence, these first two graphs, but this one has infinite valence. Every vertex has infinitely many edges connected to it. Another observation, I guess, is that the quotient of the action of the group on these trees really looks like this. As we had on my previous slide. I also want to mention that, so these first two actions, they're covering space actions. So in particular, the first two actions are free. It turns out that a group that acts freely on a tree is free. So we've just proved the Nielsen-Schreier theorem, I guess, if you accept the axiom of choice. And the second action, this action is not free, but it has trivial edge stabilizers. So an element of the free group of rank 2 will fix a vertex if it, I guess I have to name things. So maybe let's have A be the thing that translates one red edge up in this middle action. That will correspond to fixing the corresponding vertex. So it'll fix this vertex, that A, and it'll maybe do some permutation of the vertices incident to that vertex. Great. And I guess next week we'll think of graphs of groups that have trivial edge stabilizers and free vertex stabilizers as being free splittings. I apparently cannot, there we go, free splittings. So come back for Radhika's talk to hear more about that. Great, so that's our first example. Where did we get the graph on the left? The graph on the left, is that what the question was? The graph on the left is the universal cover of this graph right here. So as we saw, I guess this graph is trivalent. So this graph is 2, and I colored the vertices to sort of give you a sense of where things are coming from. Cool. So
sorry, can I just suggest that you describe what a group element that translates along a blue edge does to the furry?
Oh, yeah. The furry tree, yeah. So since the blue edges are not collapsed, if you translate this way, so maybe this vertex gets mapped to this vertex, and the action on the middle tree sends this vertex to this vertex right here, that will still act by a translation of the tree. So it'll send this vertex maybe to this vertex right here. Great. So what about non-free actions? So this is maybe a lot to take in all at once. I want to tell you about the fairy diagram for SL2Z. So this is sort of a classical object that lots of people in many areas of math care about. Its vertices are the fractions in lowest terms. So P over Q, where P and Q are relatively prime. I'm also going to allow 1 over 0, but that's the only sort of division by 0 that I'll allow. And we'll connect 2 vertices by an edge when, so if I have P over Q and M over N, I can form a 2 by 2 matrix, which has first column P and Q, and second column M and N. And if the determinant of this matrix is plus or minus 1, then I will connect the corresponding vertices by an edge. So like our favorite 2 by 2 matrix maybe is like 1, 0, 0, 1. So that says that I'm connecting 1 over 0 to 0 over 1. Great, so far so good. So there are some facts that I guess you should prove or look up or I don't know. These can be exercises if you care. They could also not be exercises if you don't care. Question mark. So every edge of this fairy diagram belongs to exactly 2 triangles. And if you draw the edges in this sort of curvilinear way, the edges don't cross each other. So sort of maybe topologically, if I removed all of the vertices from this diagram and I added faces for each of the triangles, I would get something that's a disk, like an open disk, I guess is the idea. And I can draw a tree from this data. So what I'll do is I'll add a vertex for each triangle. I could put it at the barycenter, I guess, if I'd like, if it makes sense to talk about barycenters of curvilinear triangles. And I will connect 2 vertices by an edge just when they have an edge in common in the original diagram. So I'll draw maybe a little bit of it. So there's an edge from here to here, here to here. So this tree is going to be trivalent. It will be infinite, I guess. Great. Cool. So I should keep going forever, but I don't have enough time. Awesome. So that's our second example of a tree. How does the SL2Z act on this tree?
Rylee?
Yes?
There is a question in the chat, and it says...
Is there some significance to aligning the vertices around a circle? Secretly, yes. one way you could think about this diagram is being sort of an ideal triangulation of hyperbolic two space. And so this is the like Poincare disk model for hyperbolic two space. If that means nothing to you, don't worry about it. I'm not going to use that interpretation much in these slides. But yeah. I guess there's also an action of SL2Z on the hyperbolic plane. And this sort of, the drawing it this way is secretly these actions are very closely related. That was the thing that I want to say. So SL2Z acts on this diagram. I'll tell you how it acts on the vertices. So it'll send a vertex, which corresponds to a fraction P over Q, by just multiplying. So you could think about P over Q as a column vector with P and Q. And then you just do the multiplication. So that gives you AP plus BQ over CP plus DQ. And then you just turn that back into a fraction. And then you probably want to set it in lowest terms again after that. The way that I've written, it's not obvious to me that this will be in lowest terms. So I guess what I want is put in lowest terms. So an actual exercise, but it's easy. This action on the set of vertices preserves adjacency. So it actually gives you an action on the whole diagram. So here's, and what's more, the action on the diagram gives you an action on the tree. Because we preserve adjacency, we send triangles to triangles. And so that means that we'll send the corresponding vertex to the corresponding vertex. So SL2Z acts on this tree that I'm just going to sketch a tiny bit of. Another observation to be made is that the action of a group element is entirely determined by what it does to a single triangle. So that's sort of nice. If you know something about, I guess, the action of SL2R via Mobius transformations, I guess that will tell you that things are determined by the image of a single triangle, and that you could send, say, like your favorite triangle, so maybe the one from 0, 1, infinity, you can send that to any other triangle that you would like. It turns out that if you want to act by SL2Z, there is a little bit of a restriction. There's kind of an orientation to this diagram. Maybe you could imagine, embedding it into two space and taking an orientation there. And SL2Z will preserve that orientation. So I can rotate a triangle, but I can't flip it across a vertex. Okay. So I guess another observation is that the stabilizer of a vertex will be a cyclic group of order 3. Cool. I guess another observation is that there are group elements which sends, for example, this vertex to this vertex and vice versa. So they sort of flip across this edge. Really, it's more like a rotation by 180 degrees. But that's just something that exists in this action. Cool. So it flips edges. That's my other observation. Cool. So far, so good. So that's how SL2Z acts on a tree. I want to give you 2 examples for the fundamental group of a genus 2 surface as well. So really, this first one is secretly just VanKampens theorem from algebraic topology. So what we know from VanKampens theorem is if I can cut my surface up into 2 pieces, so maybe this piece is like the right half of the surface, and I don't know, this piece will be the left half of the surface, such that their overlap is connected, then what I know is that the fundamental group is, I guess, what's called a push out. It turns out, because this curve gamma is essential, what that really means is that the fundamental group of the genus 2 surface, so pi1 of S, is isomorphic to the fundamental group of S1, free product with amalgamation, the fundamental group of S2, and the amalgamated subgroup is the infinite cyclic group corresponding to this loop gamma. So this is really, I guess, generated by gamma in some sense. So that's VanKampens theorem. I'm going to tell you a way to think about this as an action on a tree in a second, but I want to also tell you, so something that was special about this curve gamma is that it was separating, right? If I wanted to try and use VanKampens theorem on the surface on the right, where it's, I mean, it's the same surface, but I've changed the curve to be non-separating, it's clear that I can't quite use VanKampens theorem the way that I would want to. Part of that is because the overlaps would not be connected. It would be sort of two little cuffs around the boundary components. If I were to sort of cut the surface along gamma, but it is still the case that if I remove gamma and take the fundamental group of the complement, that fundamental group maps into the fundamental group of the genus 2 surface. And there is a nice relationship that we'll get to probably tomorrow. So here are my surfaces. I'm going to tell you how to build a tree that the fundamental group of the surface will act on. So here's how. I'm gonna do the classical geometric group theory thing where I'm gonna say a thing and you're gonna believe me, and I'm not gonna justify it. You can identify the universal cover of any surface of genus at least 2 with the hyperbolic plane. And so that's what I'm doing with this picture. That's why the lines are sort of curvy. And all of these red lines on the left are supposed to be lifts of this curve gamma to the universal cover. Okay, since gamma does not intersect itself, all of its lifts will be disjoint and not intersect themselves. It's, I guess, a fact about hyperbolic geometry that they'll sort of be arranged in this picture and not like, for example, if you were to take the universal cover of a torus where you would have parallel lines. And so the tree will be basically, I mean, you could think about it downstairs in the following way. So take a vertex for each complementary component and then join the bind edge if the complementary components overlap in this curve. Okay, so, and I can lift that picture to the universal cover and I will get, similarly to the SL2Z picture really, a vertex for each component of the complement of all of the red lifts. And I will have an edge from one vertex to another when they lie across, or I guess when they're separated by exactly one red lift. Okay, so this tree also infinite valence. It turns out. One reason for that, if you'd like, is that the group element corresponding to gamma, that subgroup is now normal. Each of these lifts is going to correspond to a conjugacy, a representative of the conjugacy class of gamma, and they're infinitely many because this group is infinite. Cool. Great. So this picture, actually, I can do the same thing if my curve was non-separating. So in this sense, the pictures are really the same. I can draw, again, a tree and the universal cover in precisely the same way as before. Just the quotient in the surface will now be a loop because there's one complementary component and it's connected to itself by the curve. Great, so there's also, again, another infinite valence tree. The actions, so the action of the fundamental group of the surface on its universal cover, I guess, yields an action on the tree. just because the red lines in the universal cover were exactly the lifts of the curve downstairs. So the action of the fundamental group will send lines to lines, and therefore it'll send complements of lines to complements of lines. And so you can get an action of on the tree that way. I guess an element of the fundamental group will stabilize an edge if and only if it preserves the corresponding lift of the red curve in the universal cover. So it preserves a lift of gamma. And then it's a fact about, I guess, the fundamental group of the surface. That means that that group element, G, is I guess, a power of a conjugate of gamma. Why can't I write that low, gamma? Great. Or in other words, I guess it's sort of apparent that gamma itself, or the corresponding element of the fundamental group, will preserve this line. And then it's a fact about basically surface groups that says that it and all its powers are the only things to do so. So this action on this tree is not free. In fact, its edge stabilizers are not trivial, but they are infinite cyclic. I guess you'll preserve a vertex, so you'll stabilize a vertex if you correspond to so it's, I guess, a conjugate of the fundamental group of the complement, so the surface when you subtract the curve, that will stabilize the corresponding vertex in the universal cover. So we sort of understand basically everything there is about this action on this tree, which is kind of nice. Cool. So far, so good. Great. So now I want to begin formalizing what I mean by graphs of groups. So first, I'm going to tell you too many ways to think about a graph. 3 of them, in fact, way too many. So the first definition and the definition that I think is like the best is that a graph is a one-dimensional CW complex. Okay, so that's that on that. I'm always going to think of my graphs that way. And the other ways that I'm going to tell you about are really tools to help me reason and talk about them. The first action with yes, neither action of the surface group was free. That's correct. Thank you. So my second definition of a graph is very combinatorial. It's due to Gersten, and it takes a second to get your head around it. So let's talk about it. So we're going to think of a graph as being a set, which I'll call gamma, equipped with 2 maps. So an involution on gamma, so a function from gamma to itself, such that when you square it, you get the identity, and a retraction. And the retraction, or I guess the image of the retraction, will be the fixed point set for the involution. Okay, so that's some nonsense. How do I think about that as a graph? So the fixed point set for the involution will be the set of vertices. The involution will act on that complement. So the complement will be the set of oriented edges. And the involution will just swap the orientation on the edges. So for example, what's a great graph? Here's a graph. Okay, so it has, I guess, V, W, E, and then there's, so the graph gamma SS set will be V, W, E, and I'll call it E bar. And then the involution will fix V and W and send E to E bar. Great. And then with the retraction tau, we'll send an edge, an oriented edge to its terminal vertex. Okay, so I have to pick an orientation. So let's say that E goes this way towards V. So tau of E will be V, and tau of E bar will be W. Great. So this is just like some combinatorial way to think about a graph, and I'll basically use it for convenience in terms of how I'm talking about what's going on. Great. Oh, one nice thing about this is that this allows you to us to formalize what we mean by a morphism of graphs. And I guess I'll say it just very briefly, and we'll talk about it a little bit more tomorrow. It will be a map of sets, so a function of sets from gamma to lambda that's sort of equivariant. So if I do the involution, and then I do my map F, so I'll just write what I'm saying. So if I do my involution, so this is the bar. I really cannot write that low. I'll write it over on the side. So if I do my involution, my bar, and then I do my map F, that should be the same thing as doing my map F and then doing my involution. Or in other words, it sends edges to edges, or maybe it sends edges to vertices. But if it sends an edge somewhere, it sends its the edge with the opposite orientation to the opposite orientation of the image. Sorry, that was very confusing for a very simple concept. And I also want it to be the case that the map preserves adjacency. So if I do my retraction, and then I do my map F, that should be the same thing as doing my map F, and then doing the retraction in the target. Great, so that's what a morphism of graphs is. Really, it just sends vertices to vertices, and it either sends edges to edges or it collapses edges to vertices. Those are the two possibilities. Cool, great. What's my third way of thinking about a graph? Oh, you guys, I'm very sorry. So a graph determines a small category. I know that this is geometric group theory and we don't necessarily love categories. So let's just break it down. It's not going to be that bad. Heffliger calls it a squall, a small category without loops, but doesn't matter. What you do is, so what is a category? It has objects and arrows, kind of like a graph, but not quite the same. So my objects will be, I'll have an object for each vertex. So here's my graph on the left-hand side, here's my graph. And I'm going to draw the category that I'm going to associate to it. Let me use permanent ink. Great. So it has an object for each of my vertices, but it's also going to have an object for each of the edges. So if you wanted to be super formal, it has objects for vertices of the barycentric subdivision. Great. Categories also always have to have identity arrows, so I'm just going to ignore those. The only other arrows that I'm going to have are going to be from an edge to the vertices that it is incident to. So since E1 was incident to U and V, I have an arrow from E1 to U and an arrow from E1 to V. Similarly for E2 and similarly for E3. So this is the category gamma. I am not going to name these arrows at this time, but I will on the next slide. Oh, so what do I do if I have loops or if I have multiple edges? Well, it's not so bad. Oh, so arrows from edges to incident vertices. Cool. Really not so bad. Okay, so let's do this graph lambda down below. So it has two vertices, V and W, and 4 edges. So E1, E2, E3, and E4. And then let's see, so E1, both of its incident vertices are V. So I'm going to require that I have two different arrows in my category. I'm really a stickler about that. E2 and E3 are both incident to V and W, and E4 was also a loop. Great, so that's the associated small category. The reason that it is for this without loops is that if you think about this as a directed graph, there's no way to make a loop by following a directed path. Great. Okay, so not so bad. So let's talk about what a graph of groups is. Okay, so the reason that I said the word category is because I wanted to say the word functor. So I'm very sorry. So a graph of groups is going to be a pair. So I'll have a gamma and a script EG. Gamma will be a connected graph. Most things that I'm going to talk about will make some amount of sense for disconnected graphs, but I don't know. We care about fundamental groups of connected spaces, so we're going to care about fundamental groups of connected graphs. So gamma is a connected graph, and the script EG is going to be a functor from the small category gamma to the category of groups with arrows monomorphisms. So that was a bunch of nonsense. All it really means is an assignment. So for every vertex, you have a group. So for every vertex V, there's a group, script EG sub V. And for every edge, notice edge, not oriented edge. Great. Okay, just so we're clear. There's a group, script EG sub E. And if I guess if E is incident to V, say I guess if the terminal vertex of E is V, then there's an injective homomorphism of groups. So I'm going to underline this. Homomorphism, which I will call iota sub E, from the group associated to E to the group associated to V. And I'm requiring that this homomorphism is injective. Cool. So for example, if my graph were this graph gamma right here, to cook up a graph of groups, I just need to give myself 3 groups. So maybe, I don't know. Maybe the fundamental group of, oh, sorry.
Are we requiring split injection? I don't know.
Absolutely not. Yeah. Split injections are in the category of groups means that your group is a direct product, and I don't want that. Or I mean, I'll allow it if it happens, but I don't want to force it. So for example, for our VanKampens theorem, we had this amalgamated free product, the fundamental group of one component, free product, the fundamental group of the other component, amalgamated along the curve that was the core curve of their intersection. And I can I guess formalize this as a graph of groups in the following way. I can set G sub V to be that fundamental group of the complement, one of them, G sub W to be the fundamental group of the other complement, and then I can set G sub E to be an infinite cyclic group, and then the maps from G sub E to G sub V, maybe. So I'm going to orient my edge this way. This could be, well, I guess the inclusion. So let me draw the picture that I have in my head so that I don't leave you behind. So I have had my genus 2 surface. I had my separating curve gamma. And it's this will really send it to gamma, thought of as an element of the fundamental group of the left-hand side. Okay. And then the other inclusion will be the same thing, just with the roll of the sides flipped. Okay. Any questions so far? So secretly, I'm like spoiling one of the punchlines. Amalgamated free products will be examples of, I guess what we'll call fundamental groups of graphs of groups. Yeah, that's right. I do want, I guess, G E bar to be equal to G to the E. Yeah, that's right. I will, I guess, I will use this notation where I write iota sub E bar to send it to the group associated to the edge to the group associated to the what is this? The origin vertex. So the terminal vertex of the in the opposite direction. Okay, cool. Good, great. Okay, so this is kind of algebraic and a little bit weird, but maybe it's not so bad. So really all it is that for associated to my graph for each vertex and each edge, I have a group. And if the edges are incident to vertices, I have group homomorphisms. Great. So the one way to do this, and a way that I was sort of hinting at already, is if you have a group G acting on a tree, I can give you a sort of quotient graph of groups. And we're going to define it in the following way. So what I want, first of all, we have to agree on something. Imagine I just have a group acting on a tree, and I want the quotient to inherit a graph structure from the tree that it was acting on, right? So if I'm going to be able to do that, I need to assume that the action is without inversions. So what that means is if I send an edge to itself, I don't flip it. If I send an edge to itself, I want it to fix the incident vertices. So a non-example was the action of, oh, I'm not even going to do it. I don't know, it'll give me a head rush. The action that I drew earlier for SLTC was not without inversions because it did flip across some edges. So this is useful because the quotient inherits a graph structure. Which is always nice. And if we were worried that this was an owner's condition, it is not. We can accomplish this by doing barycentric subdivision. So if I want to be extra careful and make sure that my action is without inversions, I can just barycentrically subdivide the tree. And then now, even if I flipped the edge, I will still preserve the barycenter of the edge. And now I won't preserve both of the sides of the edge. Yes, great. I see a little bit of something in the chat and I'm not really following, but it looks great. Great. Okay, so let's do it. So if we have an action on a tree without inversions, I'm to define a graph of groups, I need a graph and I need some groups, right? So my graph will be the quotient of the action of G on T. I'm terrible and I'm doing the left quotient because it's a left action. Actually, it's not terrible. Everybody should do this. So I have my group, my graph gamma, and I'm going to choose a spanning tree. And so what that is it's I guess a subgraph, which is a tree, and it contains it contains every vertex. This is too big. How can I make it smaller? Okay, so here's maybe a spanning tree. Notice that it contains every vertex, and it contains none of the loops that the graph has. Okay, so I'll let this be my spanning tree F. And then in my tree T, just because gamma is the quotient, I know, that I can lift F to a tree inside of T. So I'll call this F tilde, and I will highlight it. Great. Okay, so I'm gonna first define my groups on F tilde. So if V is a vertex of gamma, so here's V, I'll write V tilde for the corresponding vertex in F tilde. So there it is, great. And I'm gonna define my group associated to V to be the stabilizer of its lift. Okay, so if I have an element of G that fixes this vertex V tilde in the tree, remember the tree is sort of probably infinite, I'm only drawing a chunk of it. If I stabilize the vertex V tilde, I'll say that that will be my group associated to the vertex V. Great. So if I have an edge in F, so here's an edge. Let's orient it this way, maybe. I have a corresponding edge in F tilde, and I can define the group associated to that edge E to be the stabilizer of its lift as well. Great. So this is not so bad. Remember, I need homomorphisms of groups as well. I need this to be a functor. And so what I need is really a way to include the stabilizer of an edge into the stabilizers of the incident vertices. But let's think about it. We assumed that the action was without inversions. So what that means is that if you stabilize an edge, you stabilize the corresponding incident vertices. So that will just be my my homomorphism of groups. It will just be the inclusion. So say iota sub E will be just the inclusion of the stabilizer of E tilde into the stabilizer of V tilde. Great. Really not so bad so far. So the problem, or I guess the wrinkle, is what do I do with the rest of my edges? Remember, I can't, since I chose the spanning tree, there is no edge here, just because the graph is a tree. There are no loops, right? So the best that I can do is have one of my incident vertices in the tree. Okay, so let me redraw my quotient graph. What did it look like? It looked like this. Maybe let me just copy it. Great, copy. Paste it right here. Awesome. Okay. So I need to do something with the rest of my edges. In my lift, I can always choose, just because this is the quotient graph, I can choose an edge. Okay, so let's call this E prime. I can choose an edge such that its terminal vertex belongs to my lift of my spanning tree. So this was F tilde. This is going to be E prime tilde. Okay. Great. So I wrote that confusingly here as saying that the terminal vertex of my lift is the lift of the terminal vertex. Okay. And I'm going to do the same kind of thing. I'm going to define the group associated to that edge to be its stabilizer, or the stabilizer of its lift. And I have one of my inclusions for free. If I stabilize this guy right here, then I also stabilize its incident vertex. So I have an inclusion that will give me an injective homomorphism of groups. Great. But what do I do about my other guy? So I have tau of E tilde bar. And let's see, it really is secretly, it's in the same orbit as this guy, this W tilde, right? So there is some element of my group which sends this vertex right here to W tilde. I'm calling that G in what I've written so far. And I can do the following thing. So I noticed that if H stabilizes E tilde, then G inverse. Okay, let's look at what it does to W tilde. So G inverse takes W tilde to this guy right here. H fixes this whole edge, so it fixes this guy as well. And G will send me back to W tilde. So GHG inverse stabilizes the correct lift. How did I write that? Tau of E prime tilde. Okay. And this is just conjugation. So that'll, like, if I restrict to the stabilizer, that's a homomorphism of groups and it's injective. So I'm going to define, define iota of E prime bar from G E prime to GW to be H maps to, so H, remember, is something that stabilizes this edge right here. And I need something that stabilizes this vertex. And we just worked through the argument for why this guy, GHG inverse, so conjugating H by G, will stabilize the correct vertex. Great. So I have all of my graphs, all of my groups, all of the homomorphisms that I want. We did all of the things. That's great. Really quickly, let me just run through an example. So
there's a question. Are you picking orientations for the edges in the complement of F?
Yes, yeah. So this construction depends on several choices, as some of you are pointing out in the chat. It depends on a choice of orientation for the edges in the complement. There's no natural choice. You just have to make a choice. There are many possible, I guess a priori, there are many possible choices of group element that sends the wrong vertex to the right one. And so the homomorphism that you get will depend on that choice as well. So that's actually really great. So we made an observation. The quotient graph of groups depends on several choices. In particular, more than just a base point. It turns out that these choices, well, I guess really what the choice really is it's a fundamental domain for the action. So what I mean is it's a subset of the tree. Let me, yeah, so in the end, what we'll have is a subset of the tree. Maybe it looks like this. So these are supposed to be my extra guys. And I know that the action on this guy minus some of the vertices is transitive. And the only places where something is sent to itself, sorry, let me not say that. Well, basically what I've done is I picked like one representative for each orbit of points in the interior, and then possibly there are 2 orbits of some of the vertices. So that's what I mean by a fundamental domain. Yeah, if I chose this fundamental domain and the associated group elements, taking my wrong vertices to my right vertices, those are all of the choices that I need to make to define the quotient graph of groups. If I made other choices, it turns out that there is a way to reconcile them, which I will maybe briefly talk about tomorrow. Cool. Can I steal my SL2Z? Great. Stealing my SL2Z. So remember what we said. We said that this action was not without inversions. So really what I want to do is replace it by its barycentric subdivision. What that really means is I'm adding one orbit of vertices, and each vertex will correspond to an edge of the Feighn diagram. Okay, great. Okay, so I should keep drawing them for forever, but I don't have the time, so I'm not going to. So the quotient, let's think about it. I can take any triangle to any other triangle. So exercise. Take any triangle to any other. To any other. And actually I can take any edge, same with edges. So I act transitively on the set of edges. So the quotient is T mod G, great, is just a line. So there will be one vertex corresponding to the midpoint of the triangles and one vertex corresponding to the midpoint of the edge. Great. So what are the graph, or the groups rather? It turns out that the stabilizer of a triangle, I guess the only thing that I can do is rotation. Okay, so the effective action is by a cyclic group of order 3. But it turns out that SL2Z, so fact, -1, 0, 0, -1 acts trivially, which you can try and convince yourself of. So everything that I'm saying is going to be slightly wrong up to an extension by a cyclic group of order 2. So really what happens is that the stabilizer of this vertex is a cyclic group of order 6. Yeah, yep, great. Let me not say that. The stabilizer of this edge is a cyclic group of order 4. And so the edge, I guess, in the fairy diagram, the stabilizer of an edge in the tree is going to be a cyclic group of order 2. And the inclusions, this will send, I guess, the generator to, I guess, 3, if you're thinking about it as a group under addition, or if it's generated by A, let's say A cubed. And it'll send the generator of the cyclic group of order 2 to the square of the generator over here. Okay, so that's what the quotient graph of groups looks like for the action of SL2Z on the tree corresponding to the fairy diagram. Great.
Sorry, can I just ask, did
yeah.
you say at some point that the quotient graph of groups does not depend on the choices?
It does depend on the choices. It depends on these choices, the choices that we made previously. So there are some group elements that it depends on, and it depends on a choice of fundamental domain in the tree.
But does it change the isomorphism?
There's a notion of isomorphism of graphs of groups, and it does not change that isomorphism type.
Okay.
Should the edge stabilizer be cyclic? Yes. It seems like it should be minus the identity. Oh, right. So the edge inversion, I've cleverly removed the edge inversion by adding a new vertex for each edge, right? So originally I had this edge inversion. Really what that will do now is it'll fix this vertex. So that's why there's a group of order 4 here. The fact that it's cyclic of order 4 is maybe surprising. It just sort of falls out from some linear algebra that you can do, and then I guess I will write that up as an exercise. I think it's a good thing to check. Great. So that was SL2Z. I did a little bit of the fundamental group of the genus 2 surface where I chose a separating curve. How much time do I have left? 5 minutes. Maybe if I have time, I will come back to another fundamental group of the genus 2 surface. But for now, let me just state the main theorem that we will sort of get familiar with tomorrow, get very comfortable with, I guess. So the fundamental theorem of Serre theory says the following thing. If you have a graph of groups, so I have my gamma and I have my G, and I choose a point in the graph, then there's a group G. I'm calling it, it's the fundamental group of the graph of groups. So the fundamental group of the graph of groups. There's a choice of base point because it really is a fundamental group. We'll think about it as in terms of like loops. And there's a tree T with an action of G on T without inversions, such that the quotient graph of groups is the graph of groups that I started with. So in other words, what this is really saying is that every graph of groups arises as a quotient graph of groups. This is sort of, I think that this is very, very cool, because what it really is saying is that you can give me whatever groups that you would like, and I can give you a new group built out of like combining them in a graph-like way. I guess the fundamental group has a combinatorially nice presentation, which is great if you like group presentations. And I guess this sort of turns Serre theory into like an inductive tool. In other words, and I'll say a little bit more about this on Wednesday. One way to prove theorems about groups that act on trees would be to prove it for what the vertex stabilizers look like, and then say that, okay, if I combine groups as vertex stabilizers along maybe a restricted class of what will be my edge stabilizers, then the theorem still holds. I guess what great. So that is the fundamental theorem. We'll meet, I guess basically we'll spend most of tomorrow sort of going backwards. We'll start with a graph of groups, and we'll think about what the Serre tree has to be and what the action has to look like. And then we'll sort of understand this fundamental group in terms of loops. Yeah, that will be the goal for tomorrow. Do I want to say anything more? No, I don't think so.